Welcome to NEC CyberWorkBench, the most mature high-level synthesis tool available. CyberWorkBench has over 20 years of R&D development and customer enhancements. CyberWorkBench comes with a complete verification and simulation environment. The largest design designed purely in C by CyberWorkBench is more than 70 million gates large. In the next few minutes you will learn how easy it is to synthesize C or System C descriptions using CyberWorkBench, and how CyberWorkBench can dramatically increase your design productivity while reducing your time to market. We will start by opening CyberWorkBench Integrated Design Environment. We will now import a project that we generated before. We can see the source code. In this case it's a fur filter written in ANSI C. The filter function does the filtering and the rounding, while the main process reads in the data and the coefficients and does the filtering. If we further scroll down, we can see the ANSI C test bench, which basically reads in the coefficient data from a file, the input data, and writes out the data to another file. We can then proceed parsing the C code. We have seen the CyberWorkBench has created a .iff file, which is just the parsed C code. We will then continue by setting the synthesis options in order to proceed with the actual synthesis. We right-click on the project folder and select Synthesis Options. We start by selecting the scheduling mode. In this case, CyberWorkBench has 3 scheduling modes: manual scheduling mode, automatic scheduling mode, and pipeline scheduling mode. We select the constraint frequency, the target frequency of our design. In this case it's 166 megahertz. And we have a look at our libraries. We selected for this synthesis a 90 nanometer technology library, and CyberWorkBench automatically generated the constraint file where we specify how many functional units we allow the synthesizer to use. We can also edit the constraint file and manually overwrite the default constraint file. In this case, the synthesizer would use 1 16-bit signed multiplier and 8 28-bit signed adders. We can decrease the number of adders that we allow the synthesizer to use, and we can easily increase the number of multipliers that we allow the synthesizer to use. This will create completely different RTLs with different area performance trade-offs, and we can easily do design space exploration in this way. We apply the changes and we close the window. We are ready to actually start synthesizing the design. We close the synthesis window and we press the synthesis button. Now Cyber has already finished synthesizing the filter, and it presents us the synthesis report, where we can, right after synthesis, understand the size of the design in terms of area and critical path, the estimated delay, the pin pairs, the net, and the state machine count. In this case 4 states plus the reset state. We can click at any of the design counts, and we can get detailed information of the actual synthesis. We also get information about timing, wire, net count, clock fanout, and routability. We can also see what is being executed in each control cycle of the state machine, clicking at the signal table option. The signal table option shows when data is actually read or written during the execution. The first state is the reset state, and the next cycle shows you each cycle of the finite state machine. In cycle 1, data is being accessed and read, and the following functional units are being used. In this case, these 3 multipliers. The next cycle, highlighted now, shows what is being accessed during this cycle, and so on. We can also click on one of these resources, and it will go back to the C code and highlight the part of the C code being executed during this cycle, finite state machine cycle. We can actually start looking at the data path by choosing the Show Data Path option in CyberWorkBench. If we open this utility, we can already see the hardware generated by CyberWorkBench, where on the left hand side we can see the finite state machine, and on the right hand side we can see the data path with the different function units. We can also see the critical path at this stage already by opening the critical path utility, and CyberWorkBench highlights the critical path in the schematic viewer. If we minimize the schematic viewer, we can also see that CyberWorkBench highlights the C code of the critical path, so that the user can go back to the C code and modify the C code to minimize the critical path. Once we are ready with the results, we can proceed by generating the RTL for our C description. We choose Verilog or VHDL. In this case we will choose Verilog, and we proceed generating HDL. It finished, and it created the Verilog. We can see that the Verilog is the main module, is named core, same as our process NC, and it created a finite state machine and a data path. We can easily do cross-probing now between the generator RTL and the C code by clicking on any lines of this Verilog code, taking us back to the C code, or from the C code clicking on any C line and jumping back to the Verilog code. CyberWorkBench will highlight all the lines that were generated from the given C line. And this is how you create Verilog from ANSYS with CyberWorkBench. Thank you for taking the time to learn more about CyberWorkBench.